Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 15th lecture of VLSI Interconnects course. Today we will be doing the time domain analysis of a lumped RLC circuit. So in the previous lecture we derived the transfer function of an interconnect which incorporates all the transmission line effects, and now we have an accurate frequency domain model for your RLC interconnect. However, the frequency domain transfer function which we derived is quite complex in terms of the terms included in it, and therefore the time domain quantities like delay and overshoots might not be represented by simple closed form expressions. Therefore, we will step back in this lecture and take up a lumped RLC circuit and do its time domain analysis. So, as I had mentioned that for a distributed RLC circuit like this, we have derived the closed form expression for the transfer function h of omega or h of s. However, what we are interested is if I have a time domain square wave or a unit step signal, what would be the response of my interconnect at the far end. So, what I have is that if I have a input signal like this. So, if this is my Vi of t, so if my Vi of t is say V dd into ut, and this is connected to my interconnect like this of length L, I know its transfer function. What I am interested in finding out is this. So, what is my V out of t? So, are there ripples present, or is it a damped output like this, or is there a delay and then there is something like this. So, we need to find out this. Now, think about this problem. So, my Vi of t is this. So, my V in of S would be V dd divided by S, and my V out of S will then be equal to my V dd of S into h of S. This is not a straightforward function of S, there are like hyperbolic terms and S appears in the root of terms here. So, this is quite complex function of S or omega. So, if from here if I want to find out what is my V out of t, this is not a straightforward job, right. We can numerically do it, and in one of the next lectures I will show you a simulation of that. When I can for a simple single interconnect I can get it. But think of the practical scenario where you have not just a single interconnect, but you have a branched interconnects, and you want to extend all the analysis that we do for a single interconnect to branch interconnects, cascading of non-uniform interconnects, and also you may. So, this is for a single interconnect, right, but what you would require is for something like this or something like this, right. All of these are RLC terms. So, in that case this approach this full complete approach will become very complicated. So, what we desire is a simple closed form expression for the interconnect delay, and so for that what we will do is that we will get a approximate two pole transfer function. To simplify the analysis, we will approximate the transfer function of your interconnect by a two-pole transfer function. For that there are two approaches. One approach is the equivalent Elmore delay, and the second approach is based on the ABCD parameter. So, the second approach is actually this. So, we will use this this HS, and from there we will that HS is based on the ABCD parameters, and from there we will do the two-pole approximation for the transfer function. But before we do that, in this lecture let us again start simple. So, to understand how different terms of R, L and C will impact the response, let us first do the time domain response for a lumped RLC circuit. So, therefore, we are stepping back to understand this complexity. We are stepping back to take a single elements for the resistor, inductance and capacitance. So, here I am representing them by R1, L1 and C1. These are now the resistance, inductance and capacitance, not per unit length quantities. What I am interested in is that if I have a unit step signal like this. So, if my Vi of t is VDD ut, in that case what would be my output? So, what will be my output? V out of t. For a simple lumped RLC circuit, we can find the closed form expression for V out of t, and that is what we will derive, and then we can infer different if impact of the resistance, inductance, relative strength of R and L on the presence of overshoots and the delay and other things. So, if I want to get the transfer function of this, the approach would remain the same. I will have V out of S as Vi input of S into H of S, and then V out of t would be we will get by taking the inverse Laplace transform of V out of S. So, my transfer function H of S is given by what? So, this will be 1 by C1s whole divided by R1 plus L1s plus 1 divided by C1s, and then if I rearrange, I will get a term like this. So, my HS is this. I can change the order here. So, I can write this in increasing orders of S. So, I will get an expression like this. So, HS is 1 divided by 1 plus R1 C1 S plus L1 C1 S square. So, if you compare with a single RC circuit, there was R1 C1 here, and because of the presence of an inductance, there is a term of S square. So, this inductance introduces the second pole, or it increases the order of your system here. In general, what I can also do is that I can write this as H of S as 1 divided by 1 plus B1s plus B2s square, and this is something which we will use in the next two lectures. So, for now we will be sticking with this representation. So, I can again rearrange the terms here, because I want to simplify H of S, so that I can write it in a manageable format where I can take the inverse. So, I can write it again like this. So, where I am taking the I am making the coefficient of S square as 1. So, I have an expression like this. Here what I can do is that I can define omega 1 square as 1 divided by L1 C1, and if I do that, my transfer function becomes h of s is equal to this term here. So, h of s is equal to omega 1 square divided by s square plus r1 c1 divided by root L1 c1 omega 1 s plus omega 1 square. Now, here this is now coming closer to a manageable form. Here what we can see is that this c and c would this c would cancel in the numerator. So, I can then write it like this. Here if I so there is this omega 1 here, omega 1 square here, there is a term here. If I manage to write something like this here, so r1 by 2 root over c1 L1, what I can then do is that I can replace this by another constant or variable. So, here I can represent this by eta 1. So, my final simplified transfer function can then be written in this form, where omega 1 is root over L1 C1 and my eta 1 is R1 by 2 root over C1 by L1. If you look at the form of this in one of the previous lectures, we had got a term like this for the attenuation part. So, there it was the resistance per unit length divided by 2 into root over C by L. So, this is now somewhat familiar if you can correlate it with one of the previous expressions that we had seen. So, what we want? We want the time domain response when the input signal V I of t is V d d u t. If I take its Laplace transform, what I have is V d d by s. So, finally, my V out of s is V in of s into h of s. V out of s can then be written like this. To simplify this, what we will do is, let us first simplify h of s. So, this is your h of s. So, let us simplify h of s in this form, a by, so in form of partial fractions. So, where S1 and S2 are the roots of the polynomial in here. So, are the roots of s square plus 2 eta 1 omega 1 s plus omega 1 square is equal to 0. And s, so if you solve this, the expression is now straightforward. So, you will get an expression like this. Here you can see that your omega 1 4 omega 1 will come out of this square root, and that 2 and 2 will cancel out, and finally, you will be getting S1 2 as this. So, your S12 would be sorry, S1 and S2, there are two roots, would be given by this. So, one is given by this thing here plus, and the second root is this. So, you have two roots now, right. So, your S1 is plus and S2 is with minus. Now, once you have this, you can write h of s in this form. You can then break this into partial fractions. It is strongly recommended that you check these equations on your own. So, here there is a term of S1 minus S2 in both these terms here. If you substitute the value of S1 minus S2 from here, what you will get is S1 minus S2 is simply this. So, your S1 minus S2 is this. If you substitute this here, your omega square would cancel with the omega here in the denominator, and finally, you will get your h of s in this form. Now, we are in a position to get V out of S. So, now I multiply this H of S with V d d by S, and again there will be terms of S into S minus 1 and S into S minus S 1 and S into S minus S 2, and again if you apply the partial fractions, you will be getting V out of S in this form. So, here now you have a term of S minus S 1 and S minus S 2, right. So, in this case now, if you then substitute this these values of S minus S 1 and S 1 into S 2 is omega 1 square. So, you will have you can then further simplify this, you can multiply this here, right. So, this will be S 1 minus S 2 divided by S 1 plus S 2, and then finally, when you simplify it further, I am skipping all the steps, I am finally writing the expression, you will be getting V out of S of this form. So, your V out of S, now you have a nice manageable expression in the Laplace domain for a simple lumped RLC circuit. For this, you can take the inverse Laplace transform. Once you do that, the first term will give you V d d into u t, and the second two terms will give you these two terms, and there will be a u t term here as well. So, here you can see that your expression is now relatively simple, but even for a simple lumped RLC case, you are getting two exponentials here, right. So, this is this and there are two exponentials for those two poles. So, here what we can do, so now what the good thing is that you have a closed form expression for V out of t. So, from this closed form expression, getting a delay will not be that straightforward. So, in some of the approaches, we fit this for different values of eta and omega 1 to get what will be your delay. So, from here, the good thing is that if you define say 50% delay, what you can get is basically what is your V out of T d is like 0.5 times V d d, and from this you can invert to get T d as a function of eta 1 and omega 1, which in turn or a function of R 1, L 1 and C 1, right. What is eta 1? Your eta 1 is R by 2 root over C 1 by L 1, and your there is space. So, your eta 1 is R 1 divided by 2 root over C 1 by L 1, and your omega 1 is equal to 1 by root over L 1 C 1. So, from here you can get the some way of getting the delay. In the next lecture, we will see that this can be curve fitting can be used to get a simpler expression for a delay for different values of eta, right. So, this simplifies our life a lot, but now based on this, let us understand and evaluate what this response would mean. So, here you can cross check at when t is equal to 0, the net thing you will get is 0. So, you can cross check, I am not doing it here, but you can cross check that this V out of t is equal to 0 when t is equal to 0. This entire thing would come out to be minus VDD, and this will be VDD at say t is equal to 0 plus. So, based on eta, eta is this. So, based on the values of eta or the range of eta, your response will be different. So, you can note here that in the denominator, in this exponent, there is this root over eta square minus 1. Depending on the value of eta, it will depend that whether this is a real number or an imaginary number. So, if your eta 1 is greater than 1, in that case your in this case your root over eta 1 square is there is square, yeah, eta 1 square minus 1 will be real, and in that case your both the roots S1 and S2 are real roots. So, this is S1 and this is S2, right. So, here in this case you can see that there is no oscillating term here, because the exponents are the e to the power terms arguments are real valued, and therefore, you will have a monotonic function, or your V out would be a increasing, is monotonically increasing. You will see the curves soon. Then there is this another case. So, this is a case 1. Then in the second case you have your eta is less than 1. In that case your eta 1 square minus 1 becomes imaginary, and your complex, I mean your roots S1 and S1 and S2 are complex, and therefore, in your output there will be ripples now, because you will have a term of e to the power some time real number plus j imaginary number, right. So, this will introduce some ripples in your output. So, your roots will then be given by this. So, this will have there will be ripples, and then there is this case 3, which is between the case 1 and case 2. In that case eta 1 is equal to 1. In that case both the roots will be equal. So, your S1 will be equal to S2. Now, if we plot these 3 cases V out, for these 3 cases you will get curves like this. So, here this would be the case where eta 1 is greater than 1, and this is the case where your output is over damped. Then this would be the case where this is critically damped, just critically damped, and then there is this case when there is an overshoot present, and this is the case of under damped. So, if you recall, we had made an argument when we had a discussion on the origin of these inductive effects, that the presence of inductance would lead to an overshoot in your output voltage. So, you can see here that there is this overshoot. So, this is the So this is the voltage overshoot. When will this happen? When your eta 1 is less than 1, or if you look at the expression for eta, when your L is large. So this will happen when L1 is large. Now, if I want to look at this in the context of say delay, suppose I want to get an idea of my 50% delay. From these three different cases, I can see that the delay for my overdamped system would be the highest. So this will be, if I want to look at this as my TD, so this will be TD3. This will be TD2 and this will be TD1. So when the or say when the resistance is less, I mean in that case also you will get an overshoot. So in that case your delay is less, right, but then there is an overshoot present. On the other hand, if I suppress the overshoot, in that case my delay increases, but then there is this case of critically damped. So this, if I were to configure the values of R, L and C in such a way that I don't want to have an overshoot, but I want to minimize the delay, this is the best I can get. If I reduce my delay any further, if I reduce my resistance any further, I will start getting overshoots or ringing in my output circuit, right. So this type of analysis is also covered in control systems and also in some basic signals and systems courses, but we now repeated this in context of this RLC circuits with emphasis on the delay and overshoots that would be present, and this will form the basis of our analysis in the next few lectures. So what we can take away from this analysis is that even though we used an expression of this form for a lumped RLC circuit, so this was for a lumped RLC circuit, but the above analysis would be valid for any HS of this form. So if I have HS of this form, this analysis would still be valid. I can even maybe take more terms and more add more terms in my exponents, and that will complicate my analysis, but that will give me better accuracy. But what we can say is that if I approximate my transfer function with a two-pole transfer function, I can get a good idea about this delay and overshoots and other things. So now the question before us is that what is H of S what are B1 and B2 for a distributed RLC interconnect model. And over next two lectures we will try to address this specific question. So to summarize, today we derived the time domain closed form expression for a lumped RLC circuit. We saw that depending on the values of R1, L1 and C1, we can predict the presence of overshoots and also get an estimate of the delays. and this analysis is valid for any system with two-pole transfer function. So, in the next lecture we will approximate two-pole transfer function for a distributed RLC model, and we will take the specific case of what is called the equivalent Elmore model. That is all for today. We will meet in the next lecture. Good day.